All right, well, the final property of a star that we need to try to measure, and it turns out this is the property, this is the physical quantity that is the most important when it comes to determining a star's entire being. That is mass. Okay, and again, mass is not how big the star is. Mass is how much matter is in the star. It's how much stuff is in the star. How many atoms, if you will, but also the mass of each, multiplying by the mass of each atom. The problem with mass is it is not easily measured. Think about it. The mass of you, usually to find your mass, what we do is we measure your weight and then convert to mass. Because on the surface of the Earth, weight and mass are proportional to each other, and we know how many kilograms equals, or how many pounds equal a single kilogram as far as weight and mass. If you stood on a different planet, you would have a different conversion factor. But the only way we do that is because of gravity. The only reason we can do that is because of gravity. If you just have an isolated object floating out in space, all by itself, there's no direct way of measuring its mass. It's kind of like if I held up a large black sphere in my hand that was about the size of a bowling ball. You would not know just by looking at it whether that sphere is as massive as a bowling ball, or maybe it's as massive as a cannonball, or maybe it's as massive as a hollow aluminum black sphere. Very low mass, in fact. It could be hollow, it could be high density, could be low density. The point is, just by looking at it, you can't tell. However, holding the ball up, I would be able to tell because I'd be measuring the pull of the Earth's gravity on that mass. In a similar way, for individual stars, it's very difficult. In fact, it's almost impossible unless you have, say, a planet orbiting around the star that you know of. It's impossible to measure the mass of that star as an individual star. So, what do? Well, we look for stars that have companions, and luckily, that is not a very difficult thing to do, because half of all the stars in our galaxy actually belong to double or multiple star systems. Okay, these systems with two stars orbiting about each other, orbiting about a common balancing point called the center of mass, they are called binary stars. Okay, so the only direct way of finding stellar mass is by observing binary stars. So this is kind of interesting, kind of a thing you should think of. There's only one way of determining the distance to stars directly, and that's geometric parallax. There's only one way of determining the mass of stars directly, and that's by observing binary stars. I suppose at this point you could also include exoplanets, because planets orbiting a star will also give you an idea of how massive that star is. But let's just stick with binary stars for now. Okay. Now it turns out the speed at which stars orbit each other, the speed at which two stars in a common celestial dance orbit each other, is dependent on two things. It's dependent on their mass, the mass of both stars, and it's also dependent on their separation. Okay, so the speed at which, or the period for which they orbit each other, depends on distance, their average separation, and their mass. Okay, so about half the stars in the universe belong to multiple star systems. The total mass of the binary system can be found using a version of Kepler's third law. Now, in the first unit, you learned about Kepler's third law when it came to planets in the solar system. We said the period squared was proportional to the average separation cubed. The only reason that worked, though, was because all the planets are orbiting the sun, and the sun is the dominant source of mass in our solar system. And so we didn't have to worry about mass, because for all the planets, the only mass that matters is the mass of the sun. Okay? When we have two objects that are more similar in mass than the sun and a puny little planet, we have to use this. Okay? The total mass of the two stars orbiting about each other, mass 1 and mass 2, is equal to the average separation cubed divided by the period squared. Okay. Now the only right way this is an actual equation is if these masses are in units of the mass of the sun, okay, solar masses, if A is in astronomical units, in other words, multiples of the Earth's distance from the sun, and the period is in years, or Earth years, the time it takes the Earth to go around the sun. If you use all those units, then you have a very simple equation that tells you the mass of both stars if you know their average separation and their orbital period. So if you can measure this, and if you can measure this, you've got the mass of the two stars. Okay? But we must know the period in years and the average separation, A, in astronomical units. Well, that's all well and good as far as finding the masses of both stars, but what we'd really like to know is the mass of the individual stars. We'd like to know what is mass 1, what is mass 2. Luckily, we have another way of doing that. Once we know both masses, we can divvy up the masses by examining the orbit of the two stars about the common center of mass. Okay. Now the distance, you think about this as a kind of a balancing thing. Say you're on a seesaw, and you're on with a small child. And basically it's no fun because basically you're going down to the ground and the child is stuck up in the air. And you can't have a fun game on the seesaw. So what you do is you shimmy down the seat of the seesaw to put yourself closer to the balancing point. When you want something balanced, the heavier object has to be closer to the balancing point. And that's why we say that mass is inversely proportional to the distance to the center of mass. Okay, the distance to the balancing point. Okay. So for example, here we have an idealized situation. We have two stars, M1 and M2. M1 is closer to the center of mass, and this is the point about which both stars orbit. But M2 is farther away, so which of the two stars do you think has more mass? Well, if you said M1, you are correct. M2 is less massive, and so it is farther. The thing is, M1 times D1 is equal to M2 times D2. Or you can algebraically flip that around and say the ratio of the masses is inversely proportional to the ratio of the distances. Okay, M1 divided by M2 is equal to D2 over D1. Why is this important? Well, this is important for divvying up the mass. If we found out from Kepler's third law on the previous page how much the mass of both stars were, then how do we divvy up the mass? Well, this will give us what fraction is in this mass and what fraction of the total is in this mass. Okay. So knowing both the total mass of the pair and the fractional mass of each star, the individual masses of each star can be computed. Let me give you a really simple example, and I will not be giving you, probably won't be giving you homework problems like this or anything, but let's say from Kepler's third law, from the average separation, which would be this distance here in AUs, and the orbital period, which would be the time it takes for each star to make a single orbit, and they would have the same period because they're orbiting about each other. From that, a cubed over p squared gives us the total mass, m1 plus m2. But let's just say that m1 plus m2 is 3. 3 solar masses. So the two stars together have as much mass as 3 suns. On the other hand, m1 is half the distance to the center of mass as m2. What that means is that m1 is twice as much mass as m2. So you have both stars equaling 3 solar masses, but this one is twice as much as this. So, using fairly common sense mathematics, or arithmetic, it means that m1 is probably twice the mass of the sun, and m2 is equal to 1 times the mass of the sun. Okay, see what we're doing there? Again, this is just kind of an example to show you the reasoning behind this. Total mass, 3 solar masses, this one twice as much as this, so this one must be 2 solar masses, and this one must be 1. Okay. When we do this for the several hundred pairs of binary stars that we know of, and there's probably several thousand now that have been discovered with various satellites and things, we find that the most massive stars are somewhere between 50 to 100 solar masses. So we're going to say about 70 just to be on the safe side. The least massive stars are about 1/10 of the solar mass. So 1/10 of the solar mass is about the lightest or least massive star you can have that can still call itself a star. We think there are objects beyond 1/10 of a solar mass that are lighter than 1/10 of a solar mass, but we would call those things either brown dwarfs, or if they're down to maybe the mass of Jupiter, we would call them planets or Jovian planets. So we can only get accurate masses for a few hundred, or maybe at this point a few thousand binary stars. However, once we know the masses of stars, we can see if the mass is related to anything. And sure enough, it is. If you plot the stars of known mass and known luminosity along a diagram of luminosity versus mass, a strange thing happens, or a very tidy thing happens actually, if you just put main sequence stars along this graph. If you only plot main sequence stars and not giant stars, not supergiant stars, not white dwarf stars, you get this beautiful diagonal trend. Okay? This nice diagonal trend that basically says the more massive the star, the brighter it is. Now there's a difference in range. You go from 1/10 of the mass of the sun up to maybe 30 or 40 solar masses. But the brightness of these stars go all the way from 1,000 to 100,000 solar luminosities. So there's a much greater variation in luminosity than there is in mass. And what that means is that the luminosity of a main sequence star is a very, very strong power of the mass. A very high power of the mass. So this is called the mass-luminosity relationship. It's a very, very important relationship. It says that we find the strong relationship between the mass and the luminosity of main sequence stars and only main sequence stars. This relationship does not apply to giant stars, does not apply to white dwarfs, does not apply to supergiant stars. And if you fit a line to this graph, the best fit would be something around m to the 3.5 power. Okay, m to the 3.5 power, by the way, if you don't have a calculator that does 0.5 powers, you can just say this is equal to m cubed times the square root of m. Okay, as long as m is in solar mass units, then L will come out in solar luminosity units. Okay. This is not an exact relationship. This is not, I mean, it is based on the laws of physics, but it is not an exact relationship. Stars are complicated things. It's what we call an empirical relationship. We see this trend among stars, but there's some scatter in this trend, and so you don't get exact numbers that way. However, what you do find is that mass is extremely important in figuring out how bright a star is, and luminosity is super sensitive to mass. So let's make a little chart. If the mass was 1 times the mass of the sun, you'd get 1 solar luminosity. Okay? If it were 2 times the sun's luminosity, it would be 2 to the 3.5 power, or 2 cubed times the square root of 2, which gives you 11.3. Now this is pretty remarkable. It means if you have a star that's twice the mass of the sun, it's not twice as bright, it's more than 10 times as bright. If you were to triple the mass of the sun, the luminosity would go up to 47 times. So that's almost 50 times. 3 solar masses is 50 times brighter than the sun. So just a little extra mass gives you a huge amount of extra luminosity. And 4 times the mass of the sun gives you well over 100 times the luminosity, because 4 cubed times the square root of 4 is 128. Okay? So this shows that a star's energy output is extremely sensitive to mass. A little extra mass yields a lot more luminosity. Taking away a little mass will decrease its luminosity. This also means that along the main sequence, the low mass stars are here, the medium mass stars are here, and the high mass bright stars are here. Okay? So this is a good trend to try to understand. Okay, that's the end of this part. We'll continue in a moment.